In section 3.2, we were pretty much just reviewing synthetic division, and we said if you do synthetic division of some big polynomial by some x minus k, how do you know whether or not k is a zero of that big function? There were some questions that said, is k a zero of this function? We did synthetic division, and then if what? If the remainder was 0, then k is a zero of that function. And if k is a zero of the function, what is a factor of the function? Like if we found out 3 was a zero, then what had to be one of the factors? X minus 3. So if k is a zero, then x minus k has to be a factor. But still, the very last problem that we did yesterday said factor the polynomial into linear factors, and I think it was a 4-term polynomial that we couldn't factor by grouping, and grouping is the only way we know how to factor something with 4 terms. So they had to give us a little hint, and the little hint was, okay, 4 is a zero of multiplicity 2. That'll get it down from 4th degree to 2nd degree, and then we can factor farther using our traditional methods. Well, where we are today is what would we have done if they had not given us the little hint 4 is a zero of multiplicity 2? The answer is we would have to go out and find the first couple zeros on our own. So just looking at that 4th degree, well, I don't have it written down, but right here, example 6 at the top of the page, if you just told me to find the zeros of that big 4th degree polynomial and you didn't give me any idea of what to start with, I would have said, okay, let's try a 1. That doesn't work, let's try a 2. We're trying to find what makes that equal to 0, and I don't know any way to attack it other than just randomly picking numbers and praying that God sends me the right one, and I get the answer. There's a better way. The better way is called the rational zeros theorem. I want to show you one other theorem. I have them right here. I mentioned this one to you yesterday, the theorem on the exact number of zeros in a polynomial or of a polynomial. If f of x is of degree greater than 0, and if the 0 is a multiplicity m, is counted m times, then f of x has precisely n zeros. All that's really saying is the 10th degree polynomial will have 10 zeros if you count the multiplicity separately. And if you include the real zeros. It doesn't say n real zeros, it just says n zeros. So if you count the real zeros, the imaginary zeros, and anything that has more than one multiplicity, you count those multiplicities separately, then an nth degree polynomial will have n zeros. And this theorem says any polynomial function can be factored into linear and quadratic factors. I could give you a 10th degree polynomial, and this theorem tells me that it could be factored into linear times quadratic factors. It just doesn't tell me how. This tells me it's possible, but it doesn't tell me how. Here comes the how right here. This is page 215 in your book, or maybe plus or minus 1. The theorem on rational zeros of a polynomial. If the polynomial f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus on and on and on until you just get down to a constant, I'd say this is an nth degree polynomial. This is just an nth degree polynomial written in descending order. If it has integer coefficients and some fraction c over d is a rational zero in simplest form, then c is a factor of the numerator and d is a factor of the denominator. All right, let me think about that. I'm saying the fraction c over d is a zero. All zeros are not whole numbers. The one you just asked me about had 3/2 as a rational zero. According to this theorem, 3 was a factor of the constant, and 2 is a factor of the leading coefficient. What this theorem allows me to do is narrow down the pool from there are infinitely many things I could have to try, and that's horrible, just makes me want to change my major, to there's a finite number of things that I could possibly have to try in looking for the rational zeros of a function. So let's see how to apply that theorem. Number 12 on page 219 says find all the solutions of the equation, and that means real and imaginary. So if you told me to find a solution to that equation and you didn't give me any hints and I didn't know anything about the rational zeros theorem, I would go, well, let's try 1, and if that doesn't work, let's try -1, and if that doesn't work, maybe I'll try 2. But what if the answer is not a whole number? What if the answer turns out to be 7/8? I would never find that by guessing. So I have to have another method, and my other method is the rational zeros theorem. This is the way I'm going to set it up. I'm going to write the factors of the constant. The factors of 5 are just positive and -1 and positive and -5. There are 4 factors of 5 if you count those pluses or minus separately. And then I'm going to put the factors of the leading coefficient. Factors of 3 are plus or minus 1, plus or minus 3. Rational zeros theorem says all my possible rational zeros, the only ones I have to try, are all possible combinations of factors of 5 over factors of 3. Now, if there are 4 factors of 5 and 4 factors of 3, there should be 16 combinations of 5 over 3. Let's get them all down. I'm going to put the 1 over the 1 and then the 5 over the 1. Plus or minus 1, plus or minus 5. I just realized I said something totally wrong. I would be shot in a statistics class, but I'll tell you what that something is in just a second. Possible rational zeros are all combinations of these guys over these guys, 1 over 1, 5 over 1, and then 1 over 3 and 5 over 3. Which I don't know why I wrote an 8 when I said 5. So there are 8 possible rational zeros rather than 16. But, it would be 16 if these could be over those, but that's not what the theorem says. So it's just 8 possible combinations. That still seems yucky until you compare it to the alternative. The alternative was I was just going to sit there all day plugging in numbers and praying that one of them made that expression equal 0. And I might not have ever gotten the right answer. Now I've narrowed infinitely many possible choices down to only 8 possible choices. 8's a whole lot better to work with than infinity. So how am I going to tell? Those are just possible rational zeros. How am I going to tell which ones actually make this equation equal 0? Plug them in. Start with a 1. 3 times 1 is 3, minus 4 is -1, plus 7 is 6, plus 5 is not 0. 1 is not the answer. And then -1. -1 would be -3, minus 4 is -7, minus 7 is 0, plus 5 is not 0. -1 didn't work. We're going to have to do the same thing for 5, and for -5, and for 1/3, and for -1/3, and for 5/3, and -5/3. So it is yucky, but I'm going to have to, thank goodness I have a calculator, I'm going to let X be each one of those 8 numbers and see if any of them are solutions. Now, When graphing calculators were allowed in pre-calculus, I told you how to do this easily on a TI-84, and it's not using the graphing feature at all, it's just using the table feature. I haven't changed my notes to take that out. This is the only time in the whole class that I'm going to go, man, I wish I had a TI-84, because it is a little bit more of a nuisance on the homework. You literally have to, when you let X be 5, you're going to have to either in your head or on the calculator punch 3 times 5 cubed minus 4 times 5 squared plus 7 times 5 plus 5. That's going to be the biggest nuisance for not having a graphic calculator in the whole class. I'm going to go ahead and tell you that I tried all 8 of those numbers, and none of them worked. None of those 8 values were solutions. But I thought the rational zeros theorem told me one of these had to be a solution. No, that's not what the rational zeros theorem said. The rational zeros theorem said if there is a rational zero, it's going to be one of these numbers. That's all it said. If there is a rational zero, it's going to be one of these. What does that tell me about the solutions to this equation? Not necessarily imaginary, just not rational. What is not rational but yet not imaginary? There's the rational numbers and the irrational numbers. These solutions are either irrational or imaginary. They're not rational numbers. So all I can say about this is there are no rational solutions. And by rational, I don't mean logical. I mean answers that can be written as fractions. I could add myself a note. There's only irrational and or imaginary solutions. Now the whole point of that problem was just to say the rational zeros theorem is not the answer to all of our prayers. It's not the magic fix for finding a solution to all equations. It will only give you the rational solutions. If you have an equation that doesn't have rational solutions, I still don't know how to solve that yet. But it narrows down from infinitely many possibilities to only 8 possibilities that I could have to go through before I say definitively, hey, this equation doesn't have rational solutions. Let's do one that the rational zeros theorem actually helps us find a solution. Number 22. The rational zeros theorem says I want all of my factors, possible combinations of factors of 2 divided by factors of 12. It's always factors of the constant divided by factors of the leading coefficient. And so factors of 2 are plus or minus 1 and plus or minus 2. Factors of 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. This one's going to have more possible rational zeros because I have to put each of those numbers over 1, and then each of those numbers over 2, and then each of those over 3, and on down the line. 1 over 1 is just 1. 2 over 1 is just 2. And then I want to put 1 over 2 and 2 over 2. 1 over 2 is a half. 2 over 2 is 1, and I already have that written down. I don't have to write it again. 1 over 3 is 1/3. 2 over 3 is 2/3. 1 over 4 is 1/4. 2 over 4 is a half, but I already have that one written down. 1 over 6 is 1/6. 2 over 6 is 1/3, but I already have that written down. 1 over 12 is 1/12. 2 over 12 is 1/6, but I already have that written down. So how many possible rational solutions does this equation have? 2, 4, 8, 10, 12, 14, well, 1, 2, 3, 4, 5, 6, 7, 8, yeah, 16. Has 16 possible rational solutions, and as horrible as that is, it's a heck of a lot better than infinitely many rational solutions. I'd rather have 16 things to try than infinitely many things to try, and 99 times out of 100, you're not going to have to get too far down that list before you find the first one. So when I say find the first one, how do I find which one of those actually is a solution? Plug it in, or my word there was substitution. I tried a 1. 12 plus 8 minus 3 minus 2, that's not 0. I tried a -1. That didn't work. I tried a 2 and a -2. That didn't work. But I didn't have to get too far down the line before I found 1/2 was the first number from my list that actually was a solution to that equation. So a little bit of a nuisance, but I had to plug in 5 different numbers before I found the first 0. That makes the problem easier though, because if I know a half is a solution, what do I know is one of the factors of that left-hand side? A half is a solution, then what's one of the factors? X minus a half. To figure out what the other factor is, I need to use synthetic division with a half in the box. And that's not as bad as it seemed with this particular problem. I just brought down the 12 and said half times 12 is 6. 8 plus 6 is 14. A half times 14 is 7. -3 plus 7 is 4. A half times 4 is 2. -2 plus 2 is 0. If I had not come up with a 0 remainder there, that would have told me that I was wrong about this statement or I made a mistake in my synthetic division. If I'm right about this, then the remainder is going to be 0. The way that helps me is I can write this expression now as x minus a half times what other factor from the bottom row of my synthetic division? I'm dividing an x to the first into an x cubed. What power is my quotient going to start out with? X squared. So 12 is the coefficient of x squared plus 14x plus 4. And this still equals 0. And then my goal is to find all the solutions. Now I have this third degree polynomial down into linear times quadratic. How could I finish solving this? We're just going to sit here until somebody answers. Factor that further, and Actually, there's a GCF. It would make my life easier if I factored out the GCF. I'd have smaller numbers to work with. So I'm going to factor out a 2 and just put it out front. But now the quadratic factor is only 6x squared plus 7x plus 2. That's a little bit better. And just to see if this would factor further, this is the hard kind of trinomial. I'm going to multiply 2 times 6 is 12. Are there factors of 12 that have a sum of 7? Yeah, that tells me it will factor. Either I can split the middle term and go by grouping, or I need to get good at factoring that by trial and error. Just because if you practice, trial and error is faster. I'm going to try to factor it by trial and error. And I can only do that because I practiced it a lot. But regardless of what method I choose, I'm not going any farther before I check that factoring. That's my 6x squared, that's my 4x plus 3x, and that's my 2. So it's factored correctly. Now that I have it factored as completely as possible, I can set each factor equal to 0. Does 2 equal 0 give me a solution? I set that first factor equal to 0. No, I don't even have to write that down. 2 doesn't equal 0 no matter what x is. But I have x minus a half equals 0, or 2x plus 1 equals 0, or 3x plus 2 equals 0. And what 3 solutions does that give me? This would give me positive 1/2, and this would give me negative 1/2, and that would give me negative 2/3. So I solved something that I could not have solved before because none of the methods of factoring that I learned in Algebra 2 or in college algebra, wherever I learned to factor, none of those factoring methods would have helped me here if I could not have found the first rational 0 on my own. And the only way, if I had just started trying numbers randomly, I might not have ever thought to try a half. I never would have found the first rational 0. So the rational zeros theorem helps me find that first rational 0 so that I can factor something I could never factor before in order to solve something I could have never solved before. All right, we have 2 more, 26 and 30. By the way, there's a reason that you only have 4 problems in tonight's homework. They take a while. I never solved a 5th degree equation in my life. I wouldn't even know where to start. I could start randomly plugging in numbers and hoping that one of them works. Or I could use the possible rational zeros theorem to narrow infinitely many possibilities down to just a few possibilities. I think I'd rather use the rational zeros theorem. I just my factors of 6. and my factors of 3. And use those to get all possible rational zeros. All right, you go for it. Get me the list of possible rational zeros. Miss Megan, would you read me your list of possible rational zeros?
Positive negative 1.
Uh-huh.
Positive negative 1/3.
Okay.
Positive negative 2. Positive negative 2/3.
Okay.
Positive negative 3.
Mm-hmm.
Positive negative 6.
All right. I come about mine in a different order, so I'm going to make sure you got them all. 1/1, 1/3, 2/1, 2/3, 3/1, 3/3, 6/1, 6/3. Yep. That's 2, 4, 6, 8, 10, 12 possible rational zeros. Then what? Just to find the first one. I'm not going to have to plug all 12 of them in, but I'm going to have to plug enough of them in that I can find the first rational zero. And again, this is easier to do on a TI-84 than a graphing calculator, but let's see. If I plug in a 1, I'm going to have 3 minus 10 is negative 7, minus 6 is negative 13, plus 24 is 11, plus 11 is 22, minus 6 is not 0. So that's not going to work. Without me saying all this out loud, y'all grab a calculator and see if you can find the first rational zero. Let me see. 1/1, 2/1, 2/1, 2/3, 3/1, 3/3, 6/1, 6/3. What do you have that I don't?
I just missed it for some reason.
Okay, so you see it now? Okay. First rational zero. You found it already? I just feel it. I wasn't there yet, but you found 1/3 works. Just to make sure that you're right, I can do synthetic division and see if that gives me 0 for a remainder. So I'm going to trust you and then double check, trust but verify. By substitution, And let me verify that. When I do my synthetic division, I'm not missing any terms, 5, 4, 3, 2, 1, 0. I'm hoping that this doesn't end up being painful. One-third times 3 is 1. 1/3 times -9 is -3. 1/3 times -9 is -3. 1/3 times 21 is 7. Oh man, I'm so close. 9, 3, 21, 7, 18, 6. That gives me a remainder of 12 unless I've lost a sign somewhere. I'm sorry? -1 worked
It's supposed to be a -6 instead of positive.
because it is right there. Yay! And Andrew said 1 worked as well. Oh, -1 worked as well. We could either use Andrew's -1 or Laura's 1/3 to get that down from 5th degree to 4th degree. It's still 4th degree though. I'm not saying it got incredibly less painful. I'm just saying we got 5th degree down to 4th degree. So that equation now factors into, don't forget when you say 1/3 is a solution, don't forget to write x minus 1/3 as one of your factors. You don't want to lose that. And then the other factor from my bottom rule of synthetic division would be 3x to the 4th minus 9x cubed minus 9x squared plus 21x plus 18. Don't lose the fact that it's an equation. It equals 0 also. And then what? I'm gonna have to go back to my list of possible rational zeros and find another one. Andrew says that, is there a GCF? Hey, that would make life a little bit easier. There's a GCF. I'm gonna do that even before I go back to synthetic division. I'm gonna factor out a 3. But at that point, I'm going to have to go back to synthetic division. And if Andrew and Dylan have found that -1 is a solution, let me tell you why I'm writing that sentence. I wouldn't write it in my homework, I wouldn't write it on the test, but I want it in your notes because when I used to not write that sentence, I had a couple people do synthetic division with all 12 of those numbers. You don't have to do synthetic division 12 times, and that's why I'm writing by substitution. We're just plugging it in until we find another solution. We have 2 people that say -1 is a solution, so I'm going to do synthetic division. I only need to use this factor now. This is the guy that I'm trying to factor further, so I'm going to use those coefficients. We got 0 remainder, so that means that Dylan and Andrew were right. -1 is a solution, which means what's another factor of that expression? -1's a solution, then x plus 1 is a factor. My other factor is down to what degree now? Third degree. That's 1x cubed minus 4x squared plus x plus 6. And then I was hoping by now this would be down to something I could factor by grouping, but it's still not. Grouping's not going to work on that. So we're going to have to find one other solution by substitution. 2? Somebody found 2? All right. Maybe y'all should do tonight's homework as a group. Just go to the Learning Center with the calculator and try different numbers until you find what works. If 2 is a solution, then I should be able to do synthetic division with these coefficients, 1, -4, 1, 6, and get 0 remainder again. Don't lose any piece of the puzzle. Don't lose your 3, your x minus 1/3, or your x plus 1. But now we have the quadratic factor, x squared minus 2x minus 3. And thank goodness that is the easy kind of trinomial and it will factor. So I can solve an equation I would not have been able to solve yesterday. What are my solutions? -1 actually is multiplicity 2, and then 3, and then 1/3. And if you're just writing solutions to an equation, you don't have to worry about multiplicity. Multiplicity comes in when you're graphing, but you can say
x minus 2 is go back to the equation. We said it was a solution.
crap. I did exactly what I told y'all to be careful not to do. And I was fixing to find it. Believe it or not, I was fixing to find it because I was halfway into the sentence. This was a 5th degree equation. How many solutions do we have? Well, -1 is a 0, multiplicity 2. So this is 2, 3, 4. Right there, I would have gone, oh crap, I've lost a solution. And I would have found it. So I can play like I did that on purpose to illustrate how important checking is. But that really is how I got my degree in math, is checking, not from not making mistakes, but from finding my mistakes. So that should have a factor of x minus 2. And this should have a factor of x minus 2. And 2 is one of my solutions. All right. Now, in tonight's homework, that's what you have to do, and that's why you only have to do 4 problems. But I want to do one other thing, and not the other problem that's on the book, or on the notes, but I want to show you why we just learned all this. If I ask you to graph f of x equals 3x to the 5th minus 10x to the 4th minus 6x cubed plus 24x squared plus 11x minus 6. If I had given you that 5th degree polynomial as a function rather than an equation, based on what we learned Thursday and what we learned today, we could say, what's the end behavior of that graph?
So you want us to do step one, like we did.
No, you don't have one of these problems in the homework.
Oh,
You don't have specifically graph on the homework, you just have solve, but here's why we're doing this.
I don't know if we go from.
Vertical snake going uphill,
Yeah.
right? The odd degree positive coefficient, vertical snake going uphill, no more than how many squiggles in the middle?
4.
No more than 4 squiggles in the middle. And then, what did we find next? It's always easy to find a y-intercept. Just let x be 0, you get y is -6. Until we learned the rational zeros theorem, we could not have found the x-intercepts because we didn't know how to solve that when we set it equal to 0. Well, now we do know how to solve it.
It's the same thing.
Yeah, it's what we got as an answer to this. So my x-intercepts are 1/3, 3, -1, and 2. And 1/3, 3, and 2 were all of multiplicity 1, and -1 was multiplicity 2. So here's what I can do today that I could not have done before. I can say the y-intercept's -6. The x-intercepts are -1, 1/3, 2, and 3. I know it goes down to the left of the leftmost intercept. I know it goes up to the right of the rightmost intercept. What does the graph do at -1? It had even multiplicity, so it does a U-turn. It touches but does not cross. Has to come down here at least to -6. It may go down below -6. I'm not sure because I haven't had calculus yet. But it goes down at least here and then back up. What does it do at 1/3? Crosses. I don't know how far to go up, but at some point it's come back down to 2 and cross. At some point it's going to turn around and cross at 3 as well. All right, hold on just a minute. I want you to say wow one time before you leave today. And it may, the rest of that sentence may be, wow, I wish I had a graphing calculator. Oh, that wasn't good. Let me go back to what it was. On a standard window, that graph isn't so fabulous. You really can't tell what's going on without zooming out. But if I zoom out to, let's say, change my windows just to go from -3 to +3, counting by ones, and I'm going to make my y's go from -100 to +100, counting by tens. I should get a much better, ooh, look at that. That looks a whole lot like that, just done on a different scale. Pretty cool. All right, so the homework is the 4 problems at the bottom of the handout. And tomorrow by 2 o'clock, either Mallory or I will have had to have checked your note cards. One other thing I didn't mention yesterday, because we ran out of time, that piece of paper that I gave you with the directions for the note cards on it, the makeup test is going to be October 6th. I wasn't going kayaking on Friday. I'm going kayaking on Saturday. So the 6th, here's what I want to know. It's a Friday. Some of you may work. I have a meeting at 1 o'clock, so I have to be through by 1 o'clock. But if y'all wanted to sleep late or get up early and study, we don't have to start it at 7:30. We could start it at 10 or 11. Who has to go to work at some point on Friday? What time? Okay, so you could get somebody to let you, but you need to do it early so that you can go on to work quickly after. Okay. Then I will be here at 7:30, and y'all can be here. You can be here at, no. Yeah, you need to be there. Okay, I'm gonna be here at 7:30. Anybody who wants to take the test needs to be here at least by 8. I'll let you sleep in 30 minutes, but you need to be here by 8, and I will give you until 9:30. Okay? The test is 7:30 to 9:30. Anytime you want to come within that window, but at 9:30, it's over. All right. Perfect. 7:30 on the 6th.